Experiment 6, qualitative analysis, used to be called reactions in aqueous solutions because that's what you're doing. You're going to do a whole bunch of different reactions in aqueous solution. But what you're really doing is identifying an unknown cation via a method called qualitative analysis. Qualitative as opposed to quantitative because you're looking at the quality of something, not the quantity of it. Where might this come into play in the real world? Well, you're back on that side of the road with the overturned truck and it's up to you to figure out what was in that truck. The manifest was on fire or something. You can't just get it from the driver. So qualitative analysis, at least old school, was a great example of doing a whole bunch of different reactions in order to identify an unknown. The new way, of course, of doing these things for the vast majority of the time is you get a small sample of the stuff and you inject it into a gas chromatograph mass spectrometer and the computer spits out what it is. But there are times when you certainly can't do that. Aqueous solutions don't play with mass specs particularly well, for example. And so here we are. We're going to deal with aqueous solutions of an unknown cation, and you'll be able to identify the cation pretty much by matching it to a set of reactions where you do know what's in it. So you're going to do some known reactions and compare it to your unknown reaction, and the one that matches is kind of it. That's the bottom line. So qualitative analysis, again, definition here, is concerned with qualities over quantities. Qualitative analysis for compound or ion detection often involves exactly what I've been saying, reacting your unknown with a series of reactants or other reagents, sometimes in a specific order. It's sort of like a flow chart. The old way of doing this lab was a flow chart. You react with this. Does it do this or does it do this? All right, based on it doing this, then we'll react with this stuff and see, does it do this or does it do this, and so on and so forth until you get down to a known identification of the compound. That's it. So there are a variety of different reactions that are observed in the lab that will support your knowledge in the lecture. And here are the first two. So a double displacement or double replacement reaction pretty much is do-si-do in your partner if you've ever done square dancing. So the lead and the nitrate here are two components of this ionic compound. The sodium and the sulfate are two components of that ionic compound, and they're going to swap partners. The lead will go with the sulfate. Boom, there you go. The sodium will go with the nitrate. Boom, there you go. And since lead nitrate is clear and colorless in solution, and sodium sulfate is clear and colorless in solution, yet lead sulfate, insoluble compound using those solubility rules from the last lab, that's a white powder. And sodium nitrate is still soluble because it's got that alkali metal cation, and nitrate anion, no exceptions. Right? So that's a soluble compound, and it's clear and colorless. Well, that's great. So the presence of a white powder would be a nice indicator of a reaction between lead and sulfate. A white powder is also an indicator of a variety of other reactions, silver with chlorine, for example. So it's not, oh, a white powder, it's lead sulfate. No, it's that we've done a series of reactions and we've ended up with this white powder, and then we can figure out what it is. The next type of reaction that you'll be looking at in the lab, potentially, are oxidation-reduction reactions, or redox reactions. Why we don't say reduction-oxidation, I don't know, but we know oxidation-reduction reactions, or redox reactions, can again generate products that appear differently from the reactant. And it's that difference of appearance that we're looking for. We have a clear blue solution, we have a clear colorless solution, we combine them together and we end up with copper solid. Well, that's definitely something different, right? Purple solid, that's definitely something different in a clear colorless solution. Purple solid would probably dissolve in the clear colorless solution and we would end up with some purple looking liquid, but there we go. Definitely different looking products than reactants. And it's redox because, as you'll get to eventually in lecture, you probably haven't gotten there yet, copper is +2 here in copper nitrate because there are 2 -1 nitrates. Potassium's +1, iodine's -1 in potassium iodide. Copper solid, that's how it is right off the periodic table. No electrons transferred or shared. It's copper 0 charge. Iodine bonded to another iodine, that's 0 formal charge. So we've changed things. The iodine has gone from -1 to 0. The copper has gone from +2 to 0. That change in the oxidation number, that change in the number of electrons formally on those two elements indicates that an oxidation reduction reaction has occurred, because oxidation reduction reactions are electron transfer reactions. Something else that you'll observe in this lab that is beyond the scope of the course, meaning it's not taught in 151, is complex ion formation. The bottom line for complex ion formation is that for certain transition elements, giving an excess of a certain ion can solubilize, make dissolve, something that's otherwise insoluble, not dissolved. For example, if you have copper nitrate and you add ammonia to it, and in the presence of water, you get copper hydroxide, which is a solid, and then ammonium nitrate as your other product. That copper hydroxide, if you have more ammonia present, will form a complex ion, copper 4 ammoniums and 2 waters around it as a dication, copper +2, and 2 hydroxides as the anion. Aqueous. It was solid, now it's aqueous by the presence of that extra ammonia. You do that with main group elements, that doesn't happen. Magnesium hydroxide is a solid, it doesn't dissolve in water. You add extra ammonia in there, nothing else happens, okay? Certain transition elements can be solubilized by addition of other specific ions or molecules, ammonia, water sometimes, hydroxide sometimes. Amphoterism, same kind of thing. For certain transition elements, you can solubilize things that are otherwise insoluble. You can make an AQ out of something that was otherwise S, all right? Excess sodium hydroxide in the presence of zinc hydroxide solid will form this anion that in the presence of a alkali metal will certainly be soluble, because alkali metal salts are always soluble, no exceptions, table 4.1 or 4.2, whatever it was, okay? Zinc hydroxide is a solid, it's insoluble, but in the presence of excess hydroxide, you form this zinc tetrahydroxide dianion that in the presence of a cation will be soluble, regardless of what's happening, okay? Amphoterism, complex ion formation, redox reaction, or double displacement reaction, regardless, you're looking for what did it look like when it started? What does it look like when it finished? Do I have the same type of reaction, the same appearance of reaction with my unknown as I do with one of my knowns? So what are you actually doing in the lab? You're going to have an unknown cation, and then you're going to have magnesium nitrate solution, nickel nitrate solution, chromium nitrate solution, zinc nitrate solution, and silver nitrate solution. Nitrates are always soluble, no exceptions. So you're going to have solutions of these cations as the nitrates. It says it in the pre-lab, but you should pay attention. This is not just magnesium 0, like nickel 0, chromium 0, etc. It's not just metals. Okay, those wouldn't be solutions. Metals don't dissolve in water. These are the metal nitrates, so they're dissolved in water. And you are going to react each of those cations with dilute hydrochloric acid, dilute sodium hydroxide, more concentrated sodium hydroxide, and concentrated ammonium hydroxide. Make sure you don't mix up the two concentrations of NaOH. So you're going to have those cations down and reagents or your other reactant across. So you'll put 10 drops of your unknown across each of those, 10 drops of magnesium nitrate across each of those, 10 drops of the nickel 2 nitrate across in each of those, etc. And then you'll have 10 drops of hydrochloric acid in each one of these going down, 10 drops of the 0.1 molar sodium hydroxide going down here, 10 drops of the 6 molar sodium hydroxide going down here. You'll talk about molarity in a couple of chapters. It's a concentration unit. The big M means moles per liter. So this is 0.1 moles of NaOH per liter of solution. That's 6 moles of NaOH per liter of solution. 6 moles of NH4OH per liter of solution. 10 drops all the way down. And really what you're looking for is, does the zinc match your unknown? Then your unknown contains the zinc cation. Does the silver match your unknown? Then your unknown contains the silver cation. That's it. It's a relatively simple lab. The challenge for you here is to make sure that you make good observations. You can't just say, oh, this is clear. Oh, this is white. That's not good enough. Or this is blue. Can you see through it after you've mixed it? Then it's clear. Can you not see through it? Then it's cloudy. Okay, that's great. It's clear or cloudy. See through or not see through. Transparent or opaque. What color is it if you can't see through it? What color is it if you can see through it? You can see through blue water, right? When you go to Six Flags or toilet water or whatever, right? You can see through something that's blue or red or any color for that matter, or not if it has solid floating around in it that is colored. So you need to note whether it's transparent or opaque and whether it is colorless or colored. And if it's colored, what color is it? Okay, so let's test that. How would you describe the contents of this flask? It is yellow powder, yellow solid, in a clear and colorless liquid. You need to fully describe that in each of those boxes on page 54, or the data sheet, whichever page has the grid placed over it versus the data sheet. Something else to consider practically, again, you need to stir each component. You can do that with a stirring rod, clean it off, stir each of the 24 little wells, or you can use a pipette and suck the liquid in and out of the pipette in each well. Just make sure that you blow it out of the pipette as much as possible before you move on to the next one. You're not going to use 24 pipettes or stirring rods. Just make sure it's as clean as possible before you move to the next one. But don't go crazy. Don't make this lab take 1,000,000 years while you clean off the pipette and run it over to the sink and using soap and water each time. That's not necessary. Just rinse it off. All right, so here's kind of what you're going to be doing in the lab, an example. So you have your unknown, you mix it with a variety of different reagents, and you get this tube that looks like this one. What ion might it contain? It matches the copper too, so that's what it might contain. Might it be something that looks blue that you didn't test here? That's a possibility. So that's why I'm not saying it does contain copper too, and it's why you test your unknown with 4 different reagents, because the chances of you getting 4 reactions that exactly match and having it not be that cation are probably pretty slim. This was just a single test here. So the theoretical stuff here of things to think about for your lab report, well, what could go wrong? There's not a whole lot. Okay, maybe some contamination, but arguably contaminating your different wells is a mistake. Do make sure that you clean those well plates out very, very, very rigorously at the end of the lab. You should not be returning stained well plates. Half of them in the stockroom just look awful because people are returning them not clean. So clean your well plate before you return it to the front of the room. Thank you very much. See you in the next video.